All right, hello. I have a presentation that I want to share with you today. It is called Stoichiometry 3. Now, this is the third lecture in a series of lectures on stoichiometry. Now, let's just make sure we understand every time what is stoichiometry. Stoichiometry is the calculation of quantities in a chemical reaction. Now, let's not forget there is more than one type of chemical reaction, and those chemical reactions are signified by balanced chemical equations. So really what we're doing is we're looking at balanced chemical equations, and we are taking the information that is available to us from those equations, and then we will ultimately use that information to help us calculate certain quantities. Quantities like maybe the number of atoms or the number of molecules or moles or mass or volume, okay? But don't forget, is that going to involve arithmetic? Sure. So what's it ultimately going to employ? Well, we continue to talk about, we call it the line method or the fractional method, or, we're talking about conversion. We're talking about knowing where we want to start, but also knowing where we want to end up. Okay, so what do we do in stoichiometry? Well, we identify what we're given, but ultimately we know what we want to find. And the items that are going to help us, to help us put together these fractions, to help us do this math, okay, that information, those relationships or those ratios are going to come from the balanced chemical equation. So today is the day where we really want to start diving into the arithmetic of stoichiometry. All right, we want to have what we're given, but there's something that we're going to want to find. All right, so you need to know as a big picture item that in today's lesson, in today's practice problems, that will ultimately find the mass of a product, the molecules of a product, or volume to volume relationships. These are the three problems you're going to learn how to do today. Mass of a product, molecules of a product, or volume to volume relationships. You will hear us say again and again and again, we will refer to the mole ratio. We will refer to a piece of information that can be obtained from the balanced chemical equation from looking at the coefficients in a balanced chemical equation. All right? So looking at the coefficients, we're going to be able to come up with what we call the mole ratio. Now listen, big picture item. Why do we care so much about the mole? We care so much about the mole because if we have something in moles, look at all the different directions we can go. If we have a mole ratio from the equation, now listen to me very carefully, please, because this is something, if you understand this, it's going to make everything so much easier for you. This mole ratio that we're going to take from the equation, all right, is going to help us bridge the gap between what we're given and what we want. This mole ratio is going to become extremely important to us for each given equation. Okay, each equation is different, right? It has its own numbers. So for each given equation, this mole ratio will help us bridge the gap between what we're given and what we want. And I know you don't fully understand that yet, but I want to kind of give you a little bit of advice as to where we're going and what to look for. Because all of a sudden, then it's going to start making sense, especially when we put it to work. So, in this section, we will focus very heavily on mole ratios. In our what? Well, in our conversion factors. What are those fractions that we end up making? Remember, we're using the line method or the fractional method. In a typical stoichiometric problem, the given quantity is first converted to moles. All right, now I'm going to give you a little piece of advice, sort of an overall plan of attack that tends to occur again and again in these problems that we're going to do today, okay? In these problems that we're going to do today. A lot of times you'll be given something, so you'll have the given. Well, what will you do with the given? Well, typically you'll convert the given to moles of the given, okay? Well, why? Because remember, if you have moles, look at all the different directions you can go. Except given is not what you want. So what are you going to do? You're going to go from given to moles of given to moles of wanted, and then once you get in moles of wanted, then you can go pretty much any direction you want, and then you will go to the unit that you want. So that's at least 4 steps. Listen to me again. Typically, what you're given, to moles of given, to moles of wanted, and then once you get moles of wanted, what can you do? You can pretty much go in whatever direction you want to go. Big picture before we jump into the math. Mass of a product, molecules of a product, and volume to volume is what we're going to look at today. All right, but before we do, once again, do we have a plan of attack? The plan of attack has not changed. You're going to identify what you're solving for, so you're going to identify what you want. But come on, at the same time, you're going to be identifying what you're given. You're going to know what you have, and you're going to know where you want to end up every time. Number 2, you're going to remember that in these stoichiometric problems, you're very, very, very much going to be considering molar ratios that are going to be coming from the balanced chemical equation, from the coefficients. Next, you're going to rely on a balanced chemical equation. It has to be balanced. And number 4, in this particular set of problems, you're going to really begin to learn how to do multi-fraction problems. So guess what? You can use as many of them as you need to do what you need to do, but really to wind up where you want to wind up. But don't forget the big picture on that either. It's always what you want in the numerator and what you want to get rid of in the denominator. And if you will make that happen all the way across, you will start where you want to start and you will end where you want to end. But if you won't write down the units, if you won't show the work, then who knows where you're going to wind up at. Take the time to do it right, and I guarantee you it will pay dividends. All right? Now, this is a mouthful. I know it is, and you might have to read it more than once. You know, I'm not going to get on a soapbox here, but your education sometimes takes effort, and sometimes you have to read it 2 or 3 times to wrap your mind around it. But if you'll wrap your mind around this statement, the rest of these problems are going to make a lot of sense. Or maybe after you do a couple of problems, this statement will make even more sense. But listen to the way I'm going to read it. Here we go. In a typical stoichiometric problem, the given quantity is first converted to moles. Then the mole ratio from the balanced equation is used to calculate the number of moles of the wanted substance. Finally, the moles are converted to any other unit of measurement related to the mole as the problem requires. So here we go. Given, moles of given, moles of wanted, and then go wherever you want. And as you can see, that's going to require at least 4 steps. All right? All right. I think the best way to get there now is to jump in. Let's start doing some arithmetic. Let's start doing some math. Let's start thinking about units, but let's think about what we're trying to accomplish. We're using balanced chemical equations to give us information to help us solve for quantities. That's the definition of stoichiometry. So here we go. Calculating the mass of a product, so we're going to begin with mass. Ammonia, NH3, clouds are present around some planets. Calculate the number of grams of NH3 produced by the reaction of 5.4 grams of hydrogen with an excess of nitrogen. The balanced equation is, and here's your equation. Now I'm going to give you a piece of advice. Many of you need to slow down. You cannot be intimidated by a word problem. What you're going to do is you're going to look at the problem and you're going to do the same thing you always do. You're going to cut through the fluff and you're going to find out what you're given. The second you find out what you're given, you know where you're starting. This next thing is to find out what you want. Well, the second you find out what you want, you're going to know where you want to end. And then you're going to look at your equation to get the information that you need, provided it's balanced. Is it balanced? 2, 2, 6, 6. Yes, it's balanced. So what have I been given? Well, according to the problem, I know that I have this much reactant. I know that I have 5.40 grams of hydrogen. So I know where I'm beginning. Now, what do I want? Well, according to this, I want to calculate the number of grams of NH3. So I want to know how much mass my product has. Well, wasn't that the title of the problem? Calculating the mass of a product, okay? So, what am I going to do? I'm going to start, but I know where I want to end. So I'm going to do whatever I need to do to make that happen. And I'm going to use whatever relationship I need to use, but you know that at some point I'm going to use the molar ratio, because the molar ratio is the bridge between the given and the wanted. And it is specific to a specific equation. All right, so here we go. So how do we begin? Well, we begin with what we were given. So we know what we're given. We're given 5.40 grams of H2 over 1. And you're like, okay, Mr. Day, I know that. Yes. Okay, now what's the next step? Well, come on, we've already been hammering on this. Hammering. The next step is, well, I have what I'm given, but let's go to moles of given, because I can go from moles of given to moles of wanted, right? So we're not reinventing the wheel. We know how the fractional method or the line method works. We always have what we want over what we want to get rid of, and if we don't set it up that way, then we didn't set it up correctly. And I don't mean to oversimplify, but it's actually that simple. So I know that I need to have a mole, okay, so I have 1 mole of what? Well, of H2, because that's where I want to go next, right? Well, what is a mole of H2 in terms of mass? And you're like, oh, I know this, Mr. Day. I know how to do molar mass. We've already learned how to do that this year. I'm just going to go straight to the periodic table. Yes, you're going to go to the periodic table, and you're going to write down the molar mass of 1 mole of H2, which is going to be 2.0 grams of H2. Now, the real key is you're thinking as you go. So you're like, well, Mr. Day, I know I'm doing it right so far because I need for these units to cancel out. I wanted to convert from grams to moles. Awesome. Now you've gone from grams of given to moles of given, but that's not what the question asked. The question wants to know how many grams of this you have. Now, so this is where you utilize probably one of the most important fractions of all, called the molar ratio, because it's going to bridge the gap between the given and the wanted. And where is the molar ratio going to come from? It's going to come from the actual equation that you're given. So, what do I want to go to now? Well, Mr. Day, I need to go to moles of wanted, not moles of given. I need to go to moles of wanted. Well, what do I have according to this equation? According to this equation, I have 2 moles of NH3. Okay, but what is the relationship that exists within this equation? Because that's what the second lecture was all about, identifying relationships. Well, you're like, well, for every 2 of these I have, Mr. Day, I have 3 of these. Agreed. So I have 3 moles of H2. That relationship is clearly defined right here. Now, am I still doing it right? Well, I don't know. Are you checking as you go? Are moles of H2 canceling out? Yes. Now do I need to be doing the math yet? No, because we're just going to do the math all in one fell swoop. Let the units take care of the numbers, follow the units, know where you want to begin, know where you want to end, and then do the math. Look at your sig figs, and you should be in pretty good shape. Where do I want to end? Well, I can't end there. I know where I want to end. I wanted to end in grams of product. But can I go from moles to grams of product? And you're like, yeah, I can do that, Mr. Day. Yes, because once again, that just involves molar mass. So my last fraction is going to be grams of NH3 over what? Well, I need for that to be over 1 mole of NH3, because I need for those 2 to cancel out. Well, then what is 1 mole of NH3? Well, you're like, well, Mr. Day, I can look that up. I just look at the periodic table and get molar mass. And I find out that it is 17.0 grams of NH3. Yes, now the question is, did you begin here, but are you ending where you want to end? And the answer is yes, I'm ending where I want to end. Now I just need to do the math. So let's do the math. Let's just do the math together. So here we go. So what would you do? You would grab your calculator and you would just simply say, okay, 5.4 divided by 2.0. Now, whether you want to divide or multiply at this point, I don't really think it would matter, times 2 divided by 3 times 17.0 equals, and I get 30.6. Now, when I get that 30.6, now here's the key. The key is I'm going to look at all of my numbers here, and I'm going to see 3 sig figs here, 3 sig figs here, but I'm going to see 2 here, you know, so what am I going to do? Well, I think you know what to do. You're going to make this 31, what? Grams of NH3. And that's your answer. Now the question is, did you accomplish stoichiometry? And the answer is you found a given quantity. Based on what? Based on information in the equation. And what did you use to your advantage? You used the molar ratio to bridge the gap between the given and the wanted. And where did you get this molar ratio? You got this molar ratio from the chemical equation that you were given, provided it was balanced. Okay? So, given, moles of wanted, grams of wanted. Wow. Okay. Let's go to the next problem. Because as you recall, you were told you were going to learn how to do 3 different problems. And what were those 3 different problems again? Well, those 3 different problems were mass of product, which we just did, molecules of a product, and volume to volume. All right, so let's go to the next problem. Calculating molecules of a product. Now remember, if we're going to calculate the number of representative particles, ooh, that reminds me of my buddy Avogadro. Avogadro may show his face in this problem, huh? Think. All right, how many molecules of oxygen are produced when 29.2 grams of water is decomposed by electrolysis according to this balanced equation? Okay, so wade through the fluff. I know, and listen, and sometimes you'll learn something from the problem or you'll find it interesting, I truly hope. But I also know what you want to do. You want to do the same thing I probably want to do at your age. You simply want to find out what you need to do and you want to get the problem done. Well, then identify what you're given, identify what you want, identify your balanced chemical equation, and let's put stoichiometry to work. Stoichiometry being given to moles of wanted to whatever you want. So, what are we given? We're given 29.2 grams of water. This is a decomposition reaction. This are reacting. Here's our products. And then what do I want to know? I want to know how many molecules of this. Well, wait a minute. I'm given grams of this, but I want to know how many molecules. Can I do that? Yeah. What you're given, moles of what you're given, moles of what you want, and then you can go any direction you want. So, what was I given? I'm given 29.2 grams of H2O over 1. Okay, but what do I want to know? Well, okay, I want to know ultimately how many molecules of this I have, right? So what are we going to do? Well, you're like, well, Mr. Day, I need to convert this to moles of H2O, right? So I need 1 mole of H2O. Well, what's the molar mass? Well, go to the periodic table and figure it out. You know how to do this at this point. So you're going to get your 2 and your 16, right? Or that's going to end up becoming, let's see, I'm having a little senior moment here. Yeah, it's going to become 18 grams, okay, of H2O. Have to chuckle. I've shot this lecture now 3 times because I've had mess ups 3 times. I'm starting to run low on voice power. Okay, now, is this okay? Yeah, because that's going to cancel out and that's going to cancel out, and that's what we want to happen. I want to go from what I'm given to moles of given. But now what? Well, that's not going to help me find my product unless I use my bridge, unless I use the item, the molar ratio, which helps tie this all together. And where do I get the molar ratio? I get it from the equation. From what? From the coefficients, right? Okay, So what do I want to do now? I want to go to moles of wanted. So I need 1 mole of O2. Why? Because I only have 1 there. Okay, this ratio, this molar ratio is coming straight from the formula. Don't forget that. So for every 1 mole of this, how many moles of this do I have? Well, according to this equation, I have 2. So I have 2 moles of H2O. Now, are we doing good so far? Well, yeah, Mr. Dave, looks like we're doing good because that's going to cancel out with that. Now, I'm going to be honest with you. I'm going to be totally honest with you and lay it on the line. If you're the kind of person that's kind of lazy, or if you're the kind of person that wants the path of least resistance, or if you're the person just not going to show your work, then who knows where you're going to end up at, okay? Do it and do it right. And do it right the first time. And then you won't have to redo it. I mean, it only makes sense, okay? Except, am I where I need to be? And the answer is no, because that's not what I was asked to solve for. I was asked, how many molecules of this do I have? Well, you know that you can go from moles to molecules, right? So what do I really want to know? Well, you know I need to get rid of that. So what is 1 mole of O2? Well, this is where our buddy Avogadro comes into play, because he's the guy that helps us determine how many of something we have. So, oh yeah, so 6.02 times 10 to the 23rd molecules of O2, and I probably better write molecules, okay? Now what? Am I where I need to be? Yes. Did I know where I started? Sure. But do I know where I need to end? Yes. Will moles cancel out? Yes. Now what? Well, you know what. Now you're just going to do your math. You're going to do your math all the way through. And when you get your final answer, you're going to look at it and you're going to consider significant figures. Now, because this one is a little bit different, I kind of want you to solve this one on your own. I want you to go ahead and from this point forward, and I want you to come up with an answer that we can discuss in class, and we can discuss whether or not you, whether or not you understand what you're doing numbers-wise. But you should understand what you're doing concept-wise. Well, what are you doing? Given, moles of given, moles of wanted, but I better make sure I end up where I want to end up. If I want to go to Bloomington tonight for supper, probably be a good idea not to wind up in Louisville. Agreed? So I know where I'm starting and I know where I want to end. Stoichiometric, typical stoichiometric problem by definition. All right, there was one more problem type, and then we'll call this one a wrap. The one more problem type, as you know, was volume to volume relationships. Well, I bet that's going to involve 22.4 liters at some point. I bet that's going to involve STP. I bet that's going to involve Avogadro's hypotheses. I bet you're right. Okay? All right, so nitrogen monoxide and oxygen gas combine to form the brown gas nitrogen dioxide, which contributes to photochemical smog. How many liters of nitrogen dioxide are produced when 34 liters of oxygen react with an excess of nitrogen monoxide? Oh, what a mouthful. Okay, we're not going to worry about that. We're going to identify what we're given, and we're going to identify what we want. And then we are going to do whatever we need to get from point A to point B. It's the same thing every time. So we know we have 34 liters of oxygen, and we know that we really want to know how much of this we have in what? In liters. So we know how many liters we have here, but we want to know how many liters we have here. I bet this is a typical stoichiometric problem. Given, moles of given, moles of wanted, liters of wanted. So we have 34 liters of O2 over 1 times what? Well, we want to go to moles. So we want 1 mole of O2, and you already know, according to Avogadro and according to STP and according to, how many liters does O2 occupy, 1 mole of O2 occupy at STP, and you're, oh, I know that's 22.4 liters of O2. Well done. But you also had a clue before you even got started, and your clue was these had better cancel out, right? Come on, don't lose sight of the big picture. These are conversion problems, line method, fractional problems. Now what? Well, the way we've been attacking this is we've been going to moles of wanted. Well, what happens here though? Well, what happens at this stage is the very, very important fraction that comes from the equation that we call the molar ratio, which helps us bridge the gap between the given and the wanted. So I look and I say, okay, what do I want then? I want to go to moles of NO2. So I have 2 moles of NO2 for every what? For every 1 mole of O2. And where do I get that relationship? From the equation. Will moles of O2 cancel out? You bet your bottom dollar they will. Now that I'm in moles of NO2, can I go where I can go wherever I want, really, right? So now what? But that's not what I want to end up in. What? I want to end up in how many liters. So you know that I have to have liters of NO2 on top, and you know that I need to get rid of moles of NO2. This is what I say when I say let the units guide the numbers. This is going to be a 1, and this is going to be a 22.4. And what are you going to do? You're going to do your math. You know where you began, and you know where you wanted to end. So you know the unit that you're going to have at the end. Now what is your number? We'll do the math, do it all the way through. Look at your sig figs. Let's talk about it in class. Let's make sure you know what you're doing, but I think it's time and for you to have a little input as well. All right? But the process for all 3 problems has pretty much been the same, hasn't it? Given, moles of wanted, whatever you want.